Okay, I hope you can hear me.
Yeah, Professor.
Okay, great. Just let me check twice. I'm always afraid that this recording has not started. Okay, so let's see if we can speed up things a little bit here. Last time we were looking at this quantity alpha, if you remember, this quantity appearing here. Oops, okay. This quantity here, okay? And what this was essentially the sum, okay, of the difference in stoichiometric coefficients between products and reactants, okay? And we figured out that, in fact, if you consider the total number of moles, so if you have one reaction and you evaluate the total number of moles that you have at any time, this is essentially equal to the initial total number of moles, okay, plus the progress variable times alpha. So essentially, if this alpha is 0, whatever happens to the reaction, whether it's shifted to the left or to the right, really the number of moles never changes, okay? But if alpha is different from 0, in particular, if it's positive, then as the reaction proceeds from left to right, then you increase the number of moles, okay? The total number of moles. Or if it's negative, you decrease the number of moles, okay? And that is can have quite an important impact, because if you look at the equation of state here, you immediately realize that the pressure at a given volume and temperature will essentially change, okay, depending on whether the reaction proceeds from left to right, from right to left. Why? Because essentially you're adding molecules to the system. You're not adding atoms, okay? Atoms is always constant, but you're adding more molecules or less molecules, and therefore the pressure will change. And this has an effect also on the equilibrium, okay, of a system, the chemical equilibrium of a system. That is essentially the chemical equilibrium that occurs if a reaction, okay, is active between molecules in a, say, closed container. Why? Well, the very quick answer is you can have sort of a quick answer by just looking at this relationship here. Now, this doesn't tell you anything about the equilibrium clearly. It's just the equation of state. But we can sort of make a very sort of loose argument and ask ourselves what happens to psi of equilibrium, okay, if we change the pressure, okay? And well, if you have an equilibrium and you change the pressure, what you're actually doing, okay, don't ask how you change the pressure, but if you perturb the system, what you're actually doing is perturbing the system, okay? And so you're perturbing the equilibrium state, essentially, right? So by definition, this means that you're moving the system away from a minimum of Gibbs energy. So you're actually, in all intents and purposes, you are increasing the Gibbs energy, right? So suppose that, for example, your system or your reaction is such that alpha is bigger than 0, right? Well, if you increase essentially the pressure, the system, what happens? Well, if you then let it go and evolve spontaneously, well, the system will respond to reestablish, okay, a condition of minimum Gibbs energy, right? So it will respond spontaneously in a direction, therefore, to decrease G. And if alpha is bigger than 0, therefore, we will see that the psi of equilibrium will tend to decrease. It will tend to shift a little bit to the left. That is, it will try to, the system will respond spontaneously so as to fight or counteract the perturbation, okay? Which was, I remind you, an increase in pressure. So let's see this with a specific example. For example, suppose that I have a very simple reaction, okay? Which can be, it's a symbolic reaction. I won't tell you what A and B is, but let's say a reversible reaction from A to B, okay? Where A and B are some species, okay? Well, first of all, it's very easy to see that alpha, which is, I remind you, it's this quantity here. So I have to take all the species, okay, and sum on all the species. So in this case, I only have two species, A and B. So for A, this quantity here will be, well, ni double prime is 0 and ni prime is 1. So it's 0 minus 1 for species A. And for species B is simply 1 minus 0, right? And this is clearly a plus. Okay, I'm summing on all. So it's very easy to see that this is just 0. The alpha is 0. So it means that this particular reaction here, well, essentially will occur at a constant number of moles. Let's see more specifically. So the number of moles of A, by definition, is the initial number of moles of A, okay? Now, plus, clearly, ni double prime minus ni prime, which is, in this case, 0 minus 1 times psi, okay? So this would be very, very easily initial number of moles of A minus psi. And for B, okay, it's simply initial number of moles of B plus psi. So this is just a definition of progress variable, okay? Now, for simplicity, let's consider the initial number of moles of A equals to the stoichiometry. I mean, the stoichiometric coefficients. So let's take A as a reactant. So N0A will be equal to 1. And N0B, we take it equal to 0. Okay, so we only have A at first. Okay, so we know that psi will shift between 0 and 1. Okay. You can hear me, right?
Sì, sì, si sente.
Okay.
Sì, professore.
And therefore, the number of moles of A will be very simply 1 minus psi. The number of moles of B will be equal to just simply psi, right? And in fact, if you now sum, if you consider the total number of moles, this would be the sum of the number of moles of A and B. You can see that this plus this is simply 1. Okay, so it means that your total number of moles stays constant because alpha, as we said here, is equal to 0. Okay, we can also consider the mole fraction of A simply as, well, number of moles of A divided by the total number of moles. So number of moles of A is 1 minus psi divided by the total number of moles. We just saw that this is equal to 1. So this is also, sorry, this is also the mole fraction. And the mole fraction of B is simply just psi, okay? Okay, so let's take a look at what happens to the equilibrium. Okay, so the temperature is given. Okay, so T is a constant, is given. So I can calculate the equilibrium constant, which is Kp of T. So this is a number that's a constant. Okay, remember what it was? It was the exponent, okay, of minus delta G0, et cetera, divided by RT. Okay, now, what's the relationship between this reaction constant and the equilibrium composition? Well, if you remember, we had a pressure, okay, a total pressure to the power of our usual, okay, difference. So this would be alpha, okay, times, well, what we called Kx, okay, which is the product of all the the mole fractions to the power of the difference of the stoichiometric coefficients, okay? And in fact, this quantity here, we just saw that it's 0, right? So it's, I can rewrite it here as, for A, it's 0 minus 1, and for B is simply 1 minus 0. So this is P to the power of 0 times Kx, okay? So this is simply Kx. So this reaction here is clearly independent of pressure, okay? Because this vanishes. And this quantity here is the product of all the mole fractions, okay, to the power of this quantity here, okay? Which is, well, just take A, so the mole fraction of A to the power of 0 minus 1, okay? So it's minus 1. And B, it's simply to the power of 1 minus 0, okay? So it's to the power of 1. So this would be XB divided by XA. And if you go and look what we said before in terms of the progress variable, that would be psi over 1 minus psi. And clearly, let me remind you, these are all at equilibrium, okay? So even even these are at equilibrium, okay? So we have a very sort of straightforward relationship, okay, between essentially a constant function of temperature, which is given, equals to some function of the equilibrium, okay, of psi at equilibrium. So how do we use this to find the equilibrium point? Well, we can do it graphically, for example. Look. Okay. So if this is psi, this is the function psi divided by 1 minus psi. Okay. Now, clearly, this has an asymptote at 1. Okay. So it's something like this. Okay. Okay. Now, when is it that this function here is equal to this constant? Okay. So I will just say that this is the constant. This is the constant Kp of T. Okay. And so clearly, this point here is the equilibrium point, right? It's when this graph is equal to this number here. Okay. Now, obviously, That's graphic. Now, Kp, if you remember, is between 0 and 1 if delta G 0 is bigger than 0, if you remember. Okay? And so, for example, if suppose that this is 1, okay? So this would be delta G0 bigger than 0, okay? And this would be delta G0 clearly less than 0, okay? And, well, it's also very easy to see that if this is equal to, if Kp is equal to 1, then this number here, psi of equilibrium here, is equal to 0.5. So essentially, what this is telling us is that, so let me just finish this. So Kp is bigger than 0 if delta G0 is less than 0. So this graphically repeats what we saw the other day. So if delta G0 essentially is bigger than 0, the equilibrium will be over here. So it will be between 0 and 0.5. So it will favor the reactance, okay? So the reaction is at equilibrium more shifted towards the left, okay? And if delta G is negative, okay, Kp will be over here, okay? And so the reactance, sorry, the equilibrium will be shifted to the right and will be between 0.5 and 1. So we'll favor products, okay? And as you can see, this is valid at all pressures, okay? For every kind of pressure. Okay, so this is really repeating what we know, okay, in a graphical, very neat kind of way. Now let's repeat the same kind of thing for a different kind of reaction. For example, A that gives 2B, okay? Now you can already intuitively see that now this reaction clearly does not occur at a constant number of moles. For every mole of A that disappears, you have 2 moles of B appearing, and vice versa. Okay. So in this particular case, we'll do it very fast. So the number of moles of A is the initial number of moles plus, in this case, it's 0 minus 1, okay? So it's 0 minus 1 psi, number of moles of B is the initial number of moles. And here we have 2 minus 0 psi. So this is Na 0 minus psi, and this is Nb 0 plus 2 psi. Again, for simplicity, let's consider Na, the initial number of moles of A1 and the initial number of moles of B equal to 0. Okay, so in this case, Na would be 1 minus psi and Nb 2 psi. Okay, and in fact, the total number of moles will be equal to 1 minus psi plus 2 psi, which is equal to 1 plus psi. So you can see here now that the total number of moles is not constant as you move from left to right, okay? Again, for this system, is easy to see that the mole fraction of A is at all times, okay, equal to the number of moles of A divided by the total number of moles. So it's 1 minus psi divided by this 1 plus psi. And the total number of moles of B is 2 psi divided by 1 plus psi. Okay, so now we have all the ingredients to write down our condition of equilibrium. Okay, so at a given temperature, we have a certain equilibrium constant, and this must be equal to the pressure to the power of what? To the power of alpha, right? Of the sum, okay, of let me see if I'm yes, to the power of alpha. Which is the sum, okay, of the differences of stoichiometric coefficients. So let's see here how much it is for this case here. So for species A, it would be 0 minus 1 plus for species B is 2 minus 0. So this is clearly equal to 1, okay? Times the product of xi, okay, the usual stuff, okay, to the power of the difference of stoichiometric coefficients. So essentially we have P, okay, that's the total pressure to the power of 1, okay? So now you see that if you change the pressure, well, something is going to happen to your equilibrium, okay? And then here we have the product of xa to the power of -1, so it's 0 minus 1, and b to the power 2 minus 0. So this is xb squared. And to remind me, I mean, this is at equilibrium, okay? We can go forward here and say that if you substitute this as a function of the progress variable, okay? This would be, well, xb squared is 4 psi squared 1 plus psi squared. And this is x to the -1 will be 1 plus psi 1 minus psi. So essentially the bottom line is that you have pressure and then this function here, which is 4 psi divided by, if I'm not mistaken, 1 minus psi squared. And this is at equilibrium, okay? So now it's a little different than what we saw before. Again, if I'm not changing the temperature, look, this is constant. Okay, this is a number. Okay, so it's clear that if I'm, for example, increasing the pressure, well, this quantity here will have to decrease so as to keep this constant. So you see now that essentially the psi of equilibrium will be a function of the pressure itself. Okay. And remember, this is alpha, this quantity here, which we saw is positive and equal to 1. So let's do what we did before. Okay. So this is still a graph, okay, where we want to draw this function here. There is still an asymptote, some over here at psi equals 1. The only difference now is that you have this factor here, which is the pressure. So essentially, you have these functions that, for example, as you increase the pressure, they kind of go like this, right? So let me indicate the direction of pressure increase, okay? And so, again, as we did before, look, let me fix a value because we're for example, keeping the temperature constant. Let me fix a value of temperature, and therefore let me fix a value of Kp, right? Which is this. We call it Kp of T. Now, you can, for example, read this value of psi of equilibrium with the now addition of the fact that if we now perturb the system and we establish a new equilibrium, okay, by increasing, or better, if we perturb the system, okay, we increase the pressure, the system will automatically or spontaneously better respond so as to shift the equilibrium, okay, to lower values of psi. So you see that now the equilibrium at higher pressure, okay, has shifted more to the left, okay? As we expected, okay? So mathematically, this is straightforward because if you look at this function here, well, this is a constant because we haven't changed the temperature. And if the temperature is constant, then you're not changing Kp. Kp is a value which is constant, okay? But clearly, if we increase the pressure, we go from this pressure here to a higher pressure, then this quantity here will have to change. And in particular, will have to decrease, right? So we essentially go, we have to have a new value of psi so that the product is constant, okay? So you see that you have to be careful, and for a given reaction, or better still, given stoichiometry between different species, you have to establish whether the stoichiometry occurs at constant number of moles or not, okay? Now, mathematically, I hope it's quite clear. I mean, you can't escape from this definition here. If you want to keep this constant because the temperature is constant, then clearly if you change the pressure, you're going to have to change the value of equilibrium of psi, right? Now, the reason why psi decreases, let me just try and recap. Well, or let me try and repeat it again. When you increase the pressure, again, what you're doing is you're perturbing your system, okay? And whenever you perturb your system, what you're actually doing is essentially moving the system away from a condition of lowest possible Gibbs energy, okay? So if you remember at the beginning of the course, we called this moving, okay, the system along a manifold of constrained equilibrium. So you're actually constraining the system to a higher pressure in a metastable state. Now, if you essentially keep that pressure and you let now the system evolve spontaneously, the system will spontaneously will have to spontaneously reestablish a minimum of Gibbs energy. Okay? And so it will essentially shift its equilibrium, in this case, more to the left, okay, so as to counteract, okay, the fact that the pressure had increased, okay? Now, why to the left? Well, because alpha is positive, okay? So when alpha is positive, it means that the system, the reaction, when it shifts from left to right, it will essentially tend to increase the pressure. So the reaction will spontaneously counteract that increase in pressure by moving the other way around, okay? By moving in the opposite direction. If it had gone more to the right instead of to the left, the system essentially would have responded by sort of in a direction that would have still sort of increased even further the pressure, and therefore, instead of decreasing Gibbs energy, it would have increased it. Now, this sort of counter action, okay, which reestablishes the equilibrium, sometimes referred to as Le Chatelier's principle, okay? But really, the bottom line is this function here, okay, which has to keep constant. So if this increases, this has to decrease. Now, clearly, you can do an opposite problem, okay, where you have, for example, this problem here. We're not going to do it. Where you presumably will have alpha less than 0, and you have exactly the opposite situation where the system will respond to an increase of pressure by shifting to the right. Okay? Very good. Now, to conclude, let me shift to a new canvas, otherwise it's going to be too slow. I hope this guy okay. Okay, to conclude the first part of the course, okay, or the general topic of chemical equilibrium, I will now recap everything we said, okay, and describe what I call a full equilibrium, okay, calculation. What does it mean? What do we have to do? Okay? Numerically also, okay? And again, try to follow this particularly well, because this is something that, well, you're required to know, let's say. So we're putting essentially all the pieces together, okay? And all the notions, starting from, you know, postulational thermodynamics, all the way down to sort of a numerical technique, okay, to calculate the chemical equilibrium at a given pressure and temperature. So, how do we formulate this problem? Well, in the following very simple way, okay? So we're given a chemical system. What is a chemical system? A set of species. So symbolically, we call these species M1, M2, M, and S. So remember, NS is the number of species. Okay? So a point in this space here, okay, will give me for example, the composition, okay? So we're in sort of this NS dimensional space, so to speak, okay? What are we given? Well, we're given the number of species. We also have to be given an initial composition. So how do we define the initial composition? Simply the initial number of moles, okay? And we usually refer to these as N10, N20, and NS0. Okay? Why do we have to be given the initial number of moles? Well, not only is it's fundamental to know what kind of species are involved, but I also have to introduce within my system a set of, or a quantity of number of atoms. Okay, so I'm introducing atoms, and these cannot change anymore within the subsequent chemical reactions that will take place. Okay, so I'm introducing really a fixed number of atoms, and these will have to stay constant. Okay, and of course the atoms will be each part of several molecular species. Okay, but what I'm actually doing is introducing within the system a number of elemental species that will not have to change ever. Okay. And what am I also given? Well, I'm given conditions of temperature, for example, that I'm keeping constant, and pressure. Okay. As we know, we have to, generally speaking, a point of equilibrium, we just saw, okay, could be a function of both temperature and pressure. In case you're wondering, what do you mean that you're giving me temperature as well? Isn't combustion a process, a chemical process whereby temperature increases? Definitely. But you can think of it in two different ways. You can have an adiabatic situation, for example, where you have for example, a container that does not exchange heat with the surrounding. Okay. This is a slightly more complicated scenario where essentially you're keeping all the initial energy inside. Okay, you're not exchanging. So, for example, if you're doing this at constant pressure, it will be the enthalpy that will stay constant. If you remember, and so the final temperature is called the adiabatic flame temperature, and the adiabatic comes from the fact that we're not exchanging heat with the surroundings. Okay, but in a more sort of simple scenario, you can also keep the temperature constant. How do you do that? By exchanging some heat with the surroundings. So what you're doing essentially, you're subtracting or cooling the system, so to speak, so that your temperature is constant. Okay, so this would be even simpler in the sense that now I'm giving you temperature and pressure. So I don't even have to calculate the temperature. All I have to calculate, okay, is the following. So this is essentially my problem. Find, okay, the composition, which is number of moles, N1, N2, and Ns of equilibrium. Okay. So that's the formulation of my problem. Okay. Again, let me underline the fact that one of the first things, one of the most important things that you have to know is formulating the problem. Okay. Very simple. Given the number of species, given an initial composition, okay, and given the conditions of temperature and pressure, which I keep constant, okay, find Ns number of moles of equilibrium. Okay, so my unknowns, okay, are Ns. I can call them Ni of equilibrium, okay? So how many equations do we need? We need NS equations. Okay, let me underline this. So the methodology here to describe the full equilibrium calculation will amount to essentially writing down those NS equations, okay? It could be, for example, a system of hydrogen, oxygen, and water, okay? You clearly have to have a system of reactants and at least a product, okay? But you can also have intermediate species, such as OH, for example, or HO2. But for the simplest possible system would be, for example, hydrogen, oxygen, and water. So 3 species, so NS is equal to 3. So essentially, we need 3 equations, okay? Of course, equations in the unknowns, N1, N2, and 3, okay? So we're generalizing now to NS kind of equations, okay? Now, a long story short, where do we get these equations? Okay, let's see. Well, what kind of principles, okay, are we enforcing here at equilibrium? Well, we have to enforce, as we know now, 2 basic principles, okay? Conservation of atoms, okay? How many equations or relations can I write down to establish this principle? Well, if we have Ne elements or Ne elemental species, in the case of hydrogen and oxygen, atomic hydrogen and atomic oxygen, okay? These are the elements. We have essentially Ne relations or equations. Okay? The rest of the equations, okay, will come from the fact that we have to enforce a minimum of Gibbs energy, okay? So from the conservation of atoms, I have Ne relations, and the remaining Ns minus Ne will come by enforcing a minimum of Gibbs energy for each independent reaction, okay? And the minimum of Gibbs energy is what we just saw, okay, before, where for each independent reaction, you enforce that the equilibrium constant is equal to P to the alpha times the product of all the mole fractions, okay? That's, and let me just write down here equilibrium just to remind myself that this is the composition of equilibrium, okay? Now, this is clearly the statement of the problem, okay? And I'm really racing far ahead. Now, let's see how we can formulate the problem more specifically, okay? So we know that the composition N, okay, which is a vector, okay? It's a vector N1, Ns. Those are the components, okay? It cannot be anywhere, okay, in the RNS space, okay? But it needs to be restricted, or it's subject to a constraint, which is the conservation of elements. So let's say that N is constrained by the conservation of atomic species or elements. How do we write this? Well, we already know how to write this because if you remember, there exists a matrix A, okay, whose elements, let me write this as in an elemental fashion as AJ, okay? See, these are the elements of the matrix A, okay? And this is what? It's an element, it's a matrix which has NE rows and NS columns. Remember that? And it contains, each element contains numbers which represents the number of atoms, number of atoms of element I in species J. So A, essentially, to remind yourself, okay, will be essentially a matrix which is wider than it is, generally speaking, tall, okay, something like this, okay, where each row represents an element. So an atom, a kind of atom. So for example, atom 1 or element 2, and each column represents the species. So M1, M2, M3, and so on, okay? So if you have hydrogen and oxygen, what you do, for example, here, you associate, for example, the first row to the hydrogen atom, the second row to the oxygen atom, and then this will be, for example, the molecular species hydrogen, the molecular species oxygen, molecular oxygen, and the third will be H2O. And then you construct very easily this matrix by asking yourselves, how many atoms of hydrogen do I have? So the first one in H2, I have 2. How many atoms of hydrogen do I have in O2? 0. How many do I have in water? 2, etc., etc. Okay, so this would be 0, 2, and 1. Okay, and so on. Why do we need this? Because the constraint on Dn, for example, if we perturb the composition of the system infinitesimally, we know that Dn is subject to the fact that A Dn must be equal to 0. Why? Because A applied to the variation of number of moles will give me the variation of the elemental species, if you remember, which by definition must be equal to 0 because it does not have to vary ever. So when you apply matrix A to a vector of number of moles, so a composition vector, you get the number of elements, okay, the number of moles of elements. So in differential terms, these must not change, and therefore A dn must be equal to 0. And in fact, this means a very clear thing. It means that dn, okay, cannot be any vector in our phase space, but it has to be in a subspace which we call the null space or the kernel of A, if you remember, okay? Which is a subset, okay? It's a smaller dimensional, okay, than your NS dimensional space, okay? And in fact, the dimension of the kernel of A will be ns minus, okay, ne. Okay, so the way we can say this is that the span, okay, of the kernel of A, span means essentially the set of basis vectors that generate, okay, this subspace, okay, the kernel of A, is essentially composed of basis vectors which we call nu of k, okay? And k, again, the number of these basis vectors within this space is the dimension of the kernel of A. So it will be 1, 2, all the way down to ns minus ne, okay? And that is the number of possible independent reactions that you have in your system. So if you remember the hydrogen and oxygen example, we have 3 species: hydrogen, H2, O2, oxygen, okay, and H2O. We have 2 elements, H and O, and therefore I only have 1 independent reaction, okay? So in fact, my span of the kernel of A is composed only of 1 basis vector. And that direction, that basis vector, is exactly representative, okay, of the independent reaction, okay? Let's recap again. If dn is within the kernel of A, then we can express dn very simply as the linear combination of these basis vectors. So, for example, Nk from 1 to ns minus ne, okay, times some d psi of k, okay? So a linear combination, okay, of these basis vectors. So by integrating this, we could write, for example, that the composition is equal to some initial composition plus these basis vectors times, for example, psi minus psi 0. Okay? So we already seen this, all of this sort of linear algebra kind of approach, okay? So you can also see that n minus n0, okay, is a linear combination of your basis vectors, which means that if I apply now A to this vector here, by definition, I have A applied to a basis of the kernel of A, which by definition is 0, right? So if you remember graphically, we have a overall phase space, okay? And then we have an initial composition, okay, which we call N0, okay? And then you have essentially a current composition N. So essentially, okay, let's make it a little longer, okay? This N minus N0, okay, cannot be chosen arbitrarily, but it has to lie on, okay, on a plane which we call the kernel of A, okay? And it's for example, in this particular case, it's a plane. It could be anything. It could be a line. It could be a 3-dimensional phase space. It all depends on the number of species and the number of elements. Okay, and these will be your basis vectors. Okay, and so this n minus n0 has to lie on this plane here. Okay, and clearly this direction and these direction will be two independent reactions. Okay. Now the problem is, which is the equilibrium point? Do I pick this point here? Do I pick this point here or here? Well, it all depends on where the minimum of Gibbs energy will be. So we need further relations to establish that. But clearly one step, okay, towards a solution of the problem is clearly that of finding a basis vector, a basis actually, ni k, okay, with k equals 1 to ns minus ne of the kernel of A. Because this is supposed to be a k. Because if we know these vectors, well, we know where to move, okay? And each of those will represent one independent reaction. If we have this set of independent reactions, we know for sure that all of the atomic species will be conserved and that we're ready to, for each of those reactions, apply the condition of equilibrium, okay, involving an equilibrium constant and so on. Okay. So what's the first set of reactions? I'll indicate them with this arrow here. Well, the first NE, okay, equations, not reactions. Did I say reactions? I meant equation. Remember, we need, let me write here, we need NS equations. Okay. Now, the first NE equations are exactly represented by this conservation principle, okay? Well, we saw that A n minus n0, okay, is equal to 0 because n minus n0 is a vector within the kernel of A, okay? And so an is equal to an0, okay? And that, obviously, because n0 is a constant, is equal to, clearly, this is the number of moles of each element, which is a constant, okay? Why is this Ne, okay, equations? Well, this is in vector form, but remember that A, okay, is a matrix that has two rows, okay, for example, or Ne rows, okay? Two rows in the case of hydrogen and oxygen, and therefore this is essentially amounts to Ne relationships, okay, or Ne equations. So that's nice because essentially we are not guaranteed, okay, if we enforce those Ne equations, that the number of atoms is always conserved. Obviously, so we're lying on this plane here. Now, obviously, this is not enough, as I said, because we also need the remaining, okay, equations. So the remaining equations will be clearly Ns minus Ne. Okay. And how do we find those? Well, we need, oops, to find essentially the basis of the kernel of A. So these ns minus ne vectors. Why? Well, because for each of those, okay, for a given basis vector of the kernel of E, we have essentially an equation, a stoichiometric equation or a reaction, okay, which we can write down like this. Which definitely conserves atoms because it corresponds to this basis vector here, okay? Remember that, I'll write it here, okay? This vector here has components ki, which essentially are these, okay? The difference between the reactant and the product side, the product and the reactant side. Okay. And well, I have an independent reaction. It's independent because it corresponds to one of the vectors, one of the basis vectors, which by definition is an independent because they generate a vector space, which we call the kernel of A. And for each of those reactions, I can write down, okay, P to the sum, okay. I mean, I would have to write down here K and I, but it's a little bit too heavy as a notation, okay, times the product of Xi to the equilibrium to the power of Ni double prime minus Ni equals to some reaction constant, okay? And I do this, okay, for each independent reaction. Ns minus Ne, that's the number of independent reactions that I have. So the system is now essentially closed, okay? These Ns minus Ne equations will now tell me exactly where those restrict exactly the kernel of A to the point of equilibrium, okay? Which of course will lie on this plane here, but it will also satisfy the other relationships that we just wrote down, okay? Of course, I won't leave you like that, okay? I will give you an example, very brief example. Try to sort of practice a little bit. So for example, if my system has 3 species, Ns is equal to 3, and Ne, okay, the number of elements is equal to 2, okay? Well, then how many equations of the first kind do I have? How many equations of conservation do I have? Well, Ne, right? So 2. So essentially, this quantity here, these equations here are 2 equations. Okay? So each of those equations essentially is, well, a plane, okay, in R3, and this is the maximum dimension, okay, the initial dimension, but this is a restriction because I have two equations. Each of those is a plane, and the intersection is really, okay, a line, okay? And the line represents essentially my only independent reaction, because NS minus NE is equal to 1. So I only have one independent reaction. So the kernel, okay, of A is one-dimensional, okay? And the basis vector is just the one direction. And you can generalize this as much as you want. If NS is equal to 5 and NE is still equal to 2, for example, then this is a system of how many reactions? Sorry, how many equations? Well, you still have, so this is, I didn't mean to say reaction, I meant to say equations, of course. So this is a system of still, again, NE equations. Again, remember, A has only 2 rows, okay? NE, sorry, equals to 2 equations, okay? So these 2 equations will restrict our 5-dimensional space, okay, to a 3-dimensional space, okay? And so essentially now from a 5-dimensional space, we have to move around in the kernel of A, which is 3-dimensional, and S minus NE is the dimension of the kernel of A. So I only have 3 basis vectors, each of which represents an independent reaction. And so for each of those independent reactions, I will write down a condition of equilibrium. So it's much easier than you think, okay? So let me just write an example. Okay, the example is, for example, the hydrogen oxygen example. Okay, so the first thing you have to do is define your chemical system. Okay, so we assign clearly a pressure and a temperature, and then we assign the thermodynamic system, which is composed of, well, elements. I will now order them. The elements are, generally speaking, defined by the index I. So I can be 1 and 2, and clearly we're talking about hydrogen and oxygen. Okay, obviously now the number of elements, again, is 2. Okay, what about the species? Well, we assign them through our index J, okay, which, for example, now it's up to you. You can choose. You have to choose at least 3, okay? Otherwise, you don't have enough. Well, you don't have enough species to define anything. You need to have at least the 2 reactants and 1 product. But you can actually add as many as you want. You can have maybe 5, for example. The typical hydrogen and oxygen system, the minimal will have 9 species, and that's what you usually use, for example, in computational fluid dynamics codes. Okay, but in general, let's make things a little simpler here. Let's use 5. So what are they? Well, the first species is hydrogen. You can order them in any way you want, okay? But obviously, once you've decided the ordering, you can't change it, okay? So the second one will be O2. The third one is H2O. The fourth and the fifth could be other species of the system, some, for example, intermediate species. It'll be clear what I mean by intermediate when we talk about chemical kinetics. So OH, which is a radical, or an HO2, which is another radical. Okay, and clearly NS. Okay, now we've defined it as being equal to 5. Okay, and then of course I will give you the initial composition, okay, which is your vector n1, n2, etc., n5, 0. Okay, it's actually transposed because it's a column vector. Okay, so what's your now unknown of the problem? Clearly the vector n of equilibrium. That's what we have to find. So a vector composed essentially of n1 of equilibrium up to n5 of equilibrium, okay? So we need clearly 5 unknowns. Sorry, 5 equations for the 5 unknowns, okay? So what is the first thing that we have to do? Well, we first have to apply a restriction, okay, on our phase space, and we impose the conservation of atoms, which again is represented by this set of equations. How many of those do we have? Well, A, let's write it here, okay, will be a matrix, okay, which is of dimension ns by ne, okay? sorry, ne by ns, where the first one is always the number of rows, so 2 number of rows, okay? Why 2? Because clearly I equals 1 represents hydrogen and I equals 2 represents the oxygen atom, okay? On the other hand, 2, 3, 4, 5, these are the, so J equals 1, 2, 3, 4, 5, these represent the molecules, so the species, H2, O2, H2O, what was it, OH, and HO2. Okay, so you just have to now count how many hydrogen atoms do I have in all species. Well, pretty straightforward. 2, 0, 2, 1, 1. Okay, I'm counting the number of hydrogen atoms in each of those molecules. Now I have to do the same with the oxygen. It's 0, 2, 1, 1, 2. Okay? So now that I have this matrix, I can write down these restrictions, okay? And it's very easy to see that these are 2 equations, okay? You just take this matrix, okay, which is a 2 by 5, and we multiply by a 5 by 1, okay? And so we have a 2 by 1 vector. So I have essentially 2 relations. So let's write them down, okay? So 2, 0, 2, 1, 1, 0, 2, 1, 1, 2, multiplying n1, n2, etc., n5, okay, is equal to a and 0, right? So the same thing, don't let me write it again, times n0, 1, and 0, 5, okay? So I'm just writing down now in full, okay, the first of these 2 equations, which is 2n1, 2n2, plus sorry, this is not 2 and 2, this is 2 and 3, okay? Because there's a 0 here, but plus n4 plus n5, okay, is equal to, clearly it's the same thing here, so in terms of the initial number of moles, okay? Plus 2n3 plus n4. Can you hear me? Or, I mean...
Sì, sì, tutto bene.
Okay, and this must be equal to a constant. Why? Because this represents the total number of hydrogen atoms, which is constant, clearly. So that's an equation which we can call the first equation, we call it A, okay? We need 5, so A, B, C, D, and E, okay? The second one, well, take the second row here. We have essentially 0, 2, and 2, plus n3, plus n4, plus 2, n5 is equal to 2 and 0 plus n3, 0 plus n4 plus 2 and 5. And that must be equal to a constant because it's obviously this is the constant, okay? We call it NO, and it's obviously because it represents the total number of oxygen atoms, okay? And these must be always constant. So you see that these number of hydrogen atoms and this number of these numbers of oxygen, in terms of the number of moles, clearly, oxygen moles are the initial ones that I put in the system, clearly, and they won't change. So that's my second reaction, my second equation, okay? A and B. Now, what about C, D, and E? What about the remaining 3 equations? Well, these 2 equations have now operated a restriction of R5, okay? So we have, so these 2 relations operate a restriction from R5. Now we're moving to R in R3, okay? And this R3, if there is need to repeat it, is again the kernel of A, okay? Of course, well, don't let me repeat it, but A applied to n minus n0 is equal to 0, so clearly n minus n0 is equal to the kernel of A. Now, what remains to be done, okay, is to find the basis, okay, of the kernel of A. Okay? With K now, we know is just 1, 2, and 3. There's only 3 vectors, okay, which generate, okay, this 3-dimensional space, which is the kernel of A. Each of those vectors will represent, finally, an independent reaction within the kernel of A, which automatically conserves both the number of hydrogen and the number of oxygen atoms, okay? So how do we find this kernel of A? Now, I hope I have time. This basis of the kernel of A. Well, we have to find these 3 vectors, right? Ni1, Ni2, and Ni3. All of those, okay, are, well, how do you represent them? Okay, they are vectors of R5. So they have, even though they live in a subspace, you have to represent them with 5 components, right? So each one is essentially represented by 5 components, okay? Sorry. 3, 4, 5, okay? And I have clearly 3 of those, okay? Now, unfortunately, for each of those, okay, I can write down a relationship of this kind, right? Because I know that there are bases of the kernel of A, so A times any vector in the null space of A is equal to 0 by definition, right? But I have to find 5 components of each of those vectors. But how many equations does this represent? This is only 2 equations. Because remember, NS is equal to 2. This is only 2 rows, okay? So there's a trick. So it's an underdetermined kind of problem, right? Sorry, sometimes I go a little bit too fast, and then I go back. Remember, NE is equal to 2, okay? And so this can only give you 2 equations, okay? So there is a way, there's a sort of a trick, okay, that we can use. As I said, each of those basis vectors, okay, has 5 components, okay? I call those components, okay, in the following way. Let's see if I can make myself clear. I can, for example, express, well, let's use the contracted notation, okay? Each of those components, okay, of those basis vectors, I can be represented by operating a splitting of these components, okay? I will essentially separate 2 components which are in the same number of elements and 3 components here. I can only find 2, okay? Because in general, I will know those because it's an underdetermined system. All the rest of the components will be infinite to the 3, right? So I have to decide, okay, the other 3 components, what they really are. And I can actually impose, okay, that this is the canonical base, okay, in 3 dimensions. So by canonical base, I mean 0, 0, 1, 0, 1, 0, and 1, 0, 0. So in fact, okay, I can call the first 2 components a vector xk, and the rest of those components, okay, the canonical base, okay? Now, it will be quite easy now to see what I mean. So for example, suppose that k is equal to 1, okay? I will call this vector ni1 essentially like this. X1, 1, X2, let's put it up like this, 2, and then the canonical base will be 1, 0, 0. Okay, so there's probably a comma here, okay? Now, for the second vector, okay, I will call this components x2 of component 1 and 2, and then I will have these, remember, have to be independent, so I will use an independent basis here, okay, the second canonical vector. Okay. Now for 3, I'll call it x3. Okay, 1, 2, and of course 0, 0, 1. So what I'm doing I'm imposing that the last 3 components be the canonical basis vectors, okay? And I will have to find the first 2 components, okay? So in short, this is my notation, okay? So A k is equal to A applied to this vector here, xk e k, okay? Transpose, because this is a vector, a column vector. Now, how do we, and this will be equal to 0. How do we split this? Well, this is a this is a vector that has 2 components. This is a vector that has 3 components, okay? So I will also have to operate a splitting of A. How? Well, I'll have to split it this way, okay? Where I call this matrix A1 and this matrix A2, okay? In order for me to be able to multiply A1 and A2, to multiply the vector xk and ek. Okay, it's more straightforward than it actually seems. Okay, so now I'm essentially multiplying A1, which is a 2 by 2 matrix, by a 2 by 1 vector, and this is a 2 by 3 matrix by a 3 by 1 vector. Okay, so in fact, this is very simply A1 xk, okay, plus A2 ek. Now, what's the point of doing all of this? Well, these are my unknowns. Remember, this is still 2 equations, okay, because we still have 2 rows here. Sorry, 3 equations, because k is, sorry, in this case is 3 equations. So it's 1 and e minus ns, okay? So it's 1, 2, and 3, okay? But now I can actually solve it, because these are my unknowns that I keep on the left, and on the right side, I have known terms, because this is known and this is clearly known, okay? So this is my system, okay? So for each k, I will essentially now find this vector here. Let me give you an example. For the first, so this is how I split my matrix. 0, 2, what was it? 1, 1, 2. Okay, this is how I split my matrix. This is submatrix 1. This is submatrix 2. So for the first one, k equals 1, okay, this is what I have. So I have matrix A1 and A2 multiplying, okay, this vector here, x1, e1, okay, is equal to 0. So A1, x1 is equal to minus A2, e1. Okay, so let me just write it down in full and then we'll finish. So what's A1? A1 is this matrix here, so it's 2, 0, 0, 2 multiplied by x1, 1, and 2. okay? And this is equal to minus, now I have this submatrix here, 2, 1, 1, 1, 1, 2, okay? And what's this canonical vector here? It's the first one, so it's 1, 0, 0, okay? That's your first canonical vector. And this is a straightforward, clearly system in these two unknowns, and it's very, very straightforward because essentially now you can solve it and you can do it yourself, clearly. This will be -1, and this will be -1/2. Okay, so what's Ni1? We found it. The first one is -1, the second one is -1/2, and the rest is the canonical base, 1, 0, 0. Okay? Let me steal you 1 minute, okay? If you remember the ordering, the first place is hydrogen, the second place is oxygen, the third place is water, and then this is OH, and this is HO2, okay? But the thing is, now I have a stoichiometric vector. Remember, the stoichiometric vector is, represents essentially the difference between products and reactants. And so here I am. I have essentially, whenever you have a minus sign, here it is, it means that it's a product, sorry, it's a reactant. So it's 1 times H2 plus 1/2 of O2. And you see you have only water here, H2O, 1. I hope it's clear now how you can go from this to this, but you see now we have an element conserving reaction, okay, for which we can then later on write down a condition of equilibrium, okay? Now, I have to stop here, unfortunately. I never have time. I mean, with this thing, the tablet, I go half the speed. So we're going to get in trouble for some reason. I don't know why, but anyway. You can do now the opposite. Now you can go ahead and finish this. The only difference is that now your system will have, instead of having 1, 0, 0, you have a 0, 1, 0 here. Okay? So you will be introducing the OH species, and you will find another reaction. And then finally, with HO2, you have another reaction still. So now you have the 3 independent reactions, okay? Okay, I'll stop the recording.